Hello. So far we have completed several topics. So one of them is obviously the introduction, and then we have done plumes, buoyant plumes, and gravity currents. So these are two major topics apart from the introduction and dimensionless numbers and basic governing equations. We have covered. And next, we are going to cover a topic called waves. And waves are quite common in nature, especially you may have seen waves getting formed near the beaches or in the sea in particular. And so, we are going to see some basic form of wave, surface wave in particular, and we are trying to derive a simple solution. And we will try to cover this topic in very short compared to what we did for plumes and gravity currents. So this is how waves look like, and I'm sure you most have seen this kind of waves getting formed on water. So what do you see here is several different pictures, and these belong to different kind of waves that generally form in a fluid. Okay, so wave is something that you understand. This is sort of an oscillatory motion which goes up and down depending on its uh, amplitude, etc. Right? And in fluid, particularly, there are three or more kinds of waves that get created. So one of them is called surface gravity waves, then we have internal gravity waves and topographic waves, etc. So what you see here, let's call it number 1, this is number 2, and this is number 3. So these ones are the example of number 1, this is an example of number 2, and this is an example of number 3. So what's happening in case of number 1 is that there is a water surface, right, and below is all water level, and above that is air, atmospheric air, and air viscosity and density are much smaller than that of water, and that's why air properties does not really matter for water in this case, right? And that is why whenever there is some sort of disturbance or fluctuations, a wave will get created, and that will move horizontally sideward in form of wave, right, that you see in this case. In this case of this type of waves are usually popular in the sea, for example, right, that you experience when you go to the beaches. You see this kind of waves. Also, if you throw some stone in the water, in the pond or lake or even in the river, you will see this kind of waves getting created, right? So these are called surface gravity waves because this is happening at the surface, and this is the wave gets formed and propagate because of gravity effects, right? So we will see in little more detail how gravity plays a role here, but what exactly you can briefly understand is this wave that is getting created. This is all water, right, which has gone above the equilibrium level, and that is why now this water is pulled down because it is heavier than air, atmospheric air, and that gravity that is pulling it down, that creates the wave, that is surface gravity waves. Okay, so that happens purely because of gravity, right? Because water goes up and down because of gravity, right? And then there is another type of waves that's called internal gravity waves. Okay, so here again you see gravity term, but this is more related to the buoyancy effects or the density effects. So what you see here in image 2, for instance, here there is one low density fluid and another one is high density fluid. Okay, so there it might be in equilibrium initially, right? And now for some reason, let's say because of surface wave or maybe some other reason, there is some sort of disturbance in this interface between the low density fluid and high density fluid. And now when this disturbance comes in this layer, this actually creates a wave, and now this wave is getting created inside the fluid, inside water, and that is happening because of there is layer of different density, right? So this particular wave gets created in stratified medium, right? So in case of stratified medium, okay, whereas in case of gravity waves, we don't really care about stratification. We just have water layer, and above is air, which is of no significance. Okay, whereas internal gravity waves particularly form when there are stratified layer, and whenever this stratification gets disturbed, it creates waves inside the fluid layer, and that wave propagates again horizontally in sideward in form of oscillatory motion. Okay, so that is the second type of waves that get created in a fluid. And then there is another type of wave that's called topographic wave. Okay, so or you can also call it, let's say, mountain wave if it is getting created in the mountain. So what's happening here is, let's consider this example. Like there is this uniform flow that is happening from left to right, which happens in the atmosphere, right? Many times, like air flow that is coming from left to right, and it encounters a mountain. Okay, which you can see, let's say this is a mountain. So this laminar flow that is shown here, or uniform flow, that has maybe a vertical length scale of several kilometers, for instance, right? And then there is this mountain which may be in range of some meters, or maybe even a kilometer, for example. So now, because you can see there is a disturbance that is created by this mountain, so this will now, there will be some sort of uh, vorticity getting created in this flow, right? Because the flow is not straight forward, now it is getting some sort of circulatory motion because it has to change its direction. So it basically, it might be bringing some sort of circulation or some vorticity in the motion, and that actually creates this wave motion that you see. So earlier these were all parallel, now we have got this in form of wave. So we might see this sort of periodic motion after it encounters a mountain or a hill. Okay, so this kind of waves are called topographic wave, and here density is this fluid may simply be unstratified or constant density. That does not really matter here. It is happening more because of the shape of the surface rather than the density of the fluid. Okay, in our case we are mostly going to focus on the first type of wave, surface gravity waves, number one, right? And in case of number two, that is internal gravity waves, there is some similarity between one and two, but we will focus only on surface gravity waves. In what we study here may be further extended to internal gravity waves, because both these flows are driven because of density differences. Okay, so let's go a little deeper towards understanding surface gravity waves. So what's happening here? As the text says, due to some disturbance or fluctuation, for example, air turbulence, fluid mass rises above the equilibrium level, right? So let's consider that this is a solid body, solid surface, and we have water level till here, right? And there is air turbulence, right? So there is turbulence in air, and that actually tries to drive the upper layer of the fluid. Okay, or if you throw some stone or something in water, that again will disturb the equilibrium, right? So originally there was this equilibrium in water, so this is water, and now due to disturbance that is getting created, there will be some rise of mass. So this water will go up from here. Okay, it will rise till this point. Okay, now when it rises up, what happens is, this is obviously raw water, and this is rho air, where rho water is greater than rho air. So now this higher density fluid has gone into lower density medium, and that is why this gravity will try to pull it down, pull this risen fluid back to the surface, water surface level, right? And because of that, what will happen, so basically there is a some sort of delta p. So let's say this p1, this is p2, so p1 here has become greater than p2, right? So now there is some sort of fluid motion that is getting created. So that fluid that you have here in the middle, that will try to flow to the side, and in the process this red fluid basically will try to come down. So what you have here will try to come down because now it is getting space by moving off the lower layer fluid to the side, right? So when this red fluid that comes down, it comes with some sort of velocity, right? It gains velocity, it gains momentum, and by the time it reaches this original equilibrium level, it has gained already some kinetic energy, right? Some momentum, and it cannot stop there. And that is why now it goes down. Instead of stopping there, this wave will, which has gone up here, will after a certain time that will go down like this, right? Because this is the kinetic energy that it had got will convert into potential energy, and it will try to push the fluid downward, or other, sorry, the potential energy it had got will convert into kinetic energy, and that kinetic energy will push the fluid down to a negative elevation. Okay, and that is why this fluid goes down, and then it will bounce back to the same elevation or little smaller elevation. So in this way, this oscillatory motion of the fluid begins, and that creates the wave. Okay, and what happens in the process is, while it creates oscillatory motion within itself, it also pushes the fluid away from itself, like as we saw here, as this red fluid tries to, here the pressure is greater, and that's why there will be a fluid motion in this direction, and also this direction, right? So now when this fluid that you have here that pushes the fluid in the other direction, actually that waves, that energy that it has got, that will get transported to the sides in form of wave. Okay, and that is how your energy transports in form of wave from one point to the other, and this wave get created which continuously goes up and down, and that we see from the top. Okay, so waves actually transport energy, as we just saw, uh, because it pushes the fluid sideward, right? And that transports energy. But what actually happens, and that is very interesting, is that it only transports energy. It does not transport mass. Okay, it only transports energy, not mass. Okay, and to understand this, let's consider this one example here. We have a wave, this is a water wave, right, that is moving from right to left, and we have a bottle here. Okay, this is a bottle that you can see. So when wave moves from right to left, this bottle tilts, it tilts its angle. Earlier it was vertically up, now it has gone little tilted again, and once this wave comes exactly with the alignment of the bottle, it comes again vertically up. Then once waves goes to the left, it aligns towards the other side, and eventually it becomes vertical again. So what exactly happens is, when waves move from right to left or left to right, it only the waves that goes uh, backward or forward. Okay, whereas the object that you see only bobs up and down, it goes either up or down, but it does not really move sideward. And this is something you might also have seen in the ocean or in pond, or in river, when you see some, let's say, leaf for example, or some plastic, some water bottles, empty water bottle which are kept in the water, and you see a lot of tides getting created, a lot of waves getting created, but the bottle that you see from far, it just remains there, it does not really come to the shore. It will keep bobbing up or down, but it will not really move away from the position. Momentarily it will look like it's moving forward, but in the next moment it looks like it's moving backward. So it goes up, forward, backward, and as you can see, this forward and backward is basically this motion. So this point of the bottle that you see at this moment, it looks like it's moving to the left, and after a certain time it has moved to the right. So the total motion of that point is actually going from left to right, so it's actually making a circular motion at the same point. Okay, it's not really moving effectively, it just remains there. It just makes a circular motion. Okay, and this is what happens in case of a surface wave. It only transports energy, right? And that is how the waves go from one point to another, but it does not transport mass. Okay, and that is why it does not transport any pollutant or suspended matter. Okay, so if you have any sort of pollutant, let's say even if you talk about some object, as we already discussed, that will just remain there, it is not going to get transported to another place. All right, so that is the nature of surface waves. But what actually happens eventually is, this wave that is getting, that has got created, it has to break at some point of time. It cannot infinitely keep going, and while it's going, it has kinetic energy, it has momentum, but eventually it breaks because of some reasons. Let's say it goes and strikes some object, or it strikes the seashore, or it experiences some bottom friction from the surface. So there might be several reasons for breaking of the wave, and when it breaks, then this kinetic energy that it has, that converts into turbulence. In that turbulence creates mixing locally. So if there is some pollutant which is at particular place, and if that wave breaks around that point, that will create turbulence, and that will result into mixing of that pollutant in water at that particular location. Okay, so it does bring mixing of pollutants or heat, etc., but that happens within a confined region, within a small region. It does not really go with the wave. It happens when wave actually breaks, or it stops, okay, rather than moving with the wave. So there is a difference between these two. Okay, in this wave which actually especially forms near the surfaces, there is also a lot of friction coming from the bottom surface. So this actually wave result into erosion of sediments from the bottom. So that is another effect that we see because of waves. Okay, so these are some basics of waves, and let's see how this wave motion is defined, and how we can derive a solution for the wave. Okay, so we will assume that this is the bottom where z is equal to 0, and we will consider that this is x axis, this is z axis, and we have this is the water level. Okay, surface, water surface, and it creates, for some reason there is a wave that has got created. Okay, so there is a wave in at the surface, and we are trying to model this wave. Okay, and in this wave we consider that this is the depth at the equilibrium when there is no wave, that is the depth of the surface that we have, and then it creates the wave has an amplitude of capital A on both sides, and anywhere in between can be considered as a small a, which is a function of x and time, x and t. Okay, that wave distance from the equilibrium is small a, xt, that and that's a function of x and t, whereas capital A is the amplitude. Okay, so here capital A is the wave amplitude, measured from the surface at equilibrium. Okay, and we consider H to be water depth at equilibrium. All right, and A, which is function of x and t, is the wave position from water surface. Okay, so these are different behavior, we have different parameters for analyzing the wave. Okay, and now we want to solve the wave motion, this periodic motion of the wave, and we can start that using the Navier-Stokes equations, or we can call it governing equations. Okay, so we will obviously start with continuity. That will give us du by dx plus dw by dz is equal to 0. Okay, we assume in this case, let's consider that the flow is two-dimensional, because we see wave actually is generally very long and it moves in one direction, right? And that is why we will solve it as a two-dimensional problem rather than three-dimensional problem. Okay, and that is why we have uh, 2D equation where we assume that v is 0. Okay, and UWR velocity in x and z. Okay, where x is the horizontal axis and z is the vertical axis. Okay, and then we have Navier-Stokes equation in x that we can write as du by dt plus u du by dx plus w du by dz is equal to 1 by rho minus dp by dx plus mu d square u by dx square plus d square u by dz square. Okay, that is the equation we have. And then we have Navier-Stokes equation in z, which can be written as dw by dt plus u dw by dx plus w dw by dz is equal to 1 by rho dp by dz minus g, and in the previous equation there has to be rho here, sorry about that, d square w by dx square plus d square w by dz square. Okay, so these are the complete set of equations we have for solving this particular problem, given that the problem is two-dimensional and we have velocity u and w in x and z direction. Okay, and we have g term in case of z and there is no g term in case of x. Okay, but as usual we are going to make some simplification, because these three equations will be very complicated to solve for the given problem, and that is why we do linearization and some simplification. So first of all, we assume that the fluid depth to be much greater than that of the wave height or amplitude, such that we can neglect the viscous effect. Okay, so we assume viscous effects are negligible in this problem, and that is why we can consider the last term of these equations, both the equations, to be 0, or this term can be considered to be equal to 0. Okay, while viscosity itself is not 0, but viscous effects are 0. Okay, so probably this is little misleading, so I should rather just write viscous effects are 0. Okay, that is one simplification we have. And other simplification which is done in case of surface waves is that it is assumed that the non-linear terms in Navier-Stokes equation are much smaller than the linear terms. Okay, so what all non-linear terms do we see? So first, non-linear terms are obviously these viscous terms which we already assumed to be 0, right? So let's write them down. Non-linear terms are viscous terms which we are already considering to be equal to 0. Also we have these terms, right? These are the non-linear terms, right? These are, whereas this one is a linear term. Right, and why it is called linear versus non-linear? Because you can see in these non-linear terms you have two forms of velocities, where in its previous case there is just single derivative with single velocity. All right, whereas in case of viscous term we have double derivative, so that also is a form of non-linear term. Okay, so to understand the effects of non-linear term, we actually do a scale analysis. Where we'll compare du by dt with, let's compare du by dt with u du by dx. Okay, for the first equation. So du by dt can be considered to be equal to u over, let's say, t, where u is the maximum velocity and t is the time of our consideration, and u du by dx can be written as u over L. Okay, which is basically u square over L. All right, so what do we have here is that u over t is actually much greater than u square over L for a surface wave, because L is very large. Okay, so what actually happens is the length scale that is under our consideration, where waves actually does not really stop, so it goes up and down, but that does not stop there, it just keeps moving. So the concerned length scale that we have, that actually goes to really large value than the just the length scale of the wave, and that is why in this case of d by dx we have to consider the total length scale rather than just that small length scale. Okay, whereas the time scale that we are considering about is only about is of the wave, and that is why that is greater, sorry, that is much smaller compared to the L value, and that is why u over t is much greater than u square over L. Okay, and that is why we apply sort of linearization, so that all these non-linear terms, their values are actually much smaller in case of wave compared to the linear terms. Okay, and that is why the linearized governing equation we have is linearized governing equation we have is du by dx plus dw by dz is equal to 0, then du by dt is equal to minus 1 by rho dp by dx, and then dw by dt is equal to 1 by rho dp by dz minus g. Okay, so these are three equations we have, which we get after the simplification, after the linearization. Okay, in what, once again, what do you mean by linearization? We are getting rid of all the non-linear terms from the gravity, from the surface wave, because their magnitude is generally very small. So magnitude of these red terms are generally much smaller than that of the green term. Okay, so this is the set of governing questions that we are left with, and now we will seek a solution in form of sinusoidal form.